Are you guys back in the office or are you still remote?
Some of us are in the office on some days. Yes, I'm flaunting my office presence here. So yeah,
Okay.
kind of trickling in as the year progresses.
Gotcha.
All right, well, it's 11 o'clock. So as people continue to trickle in, I think I'll start introducing and start off by reminding everyone of the CGD Code of Conduct at these seminars where we offer constructive feedback and share the air, make sure that all the voices are heard, acknowledge the teamwork that goes on, encourage innovation, show appreciation, and consider new ideas. I'll also ask that everyone please keep themselves muted and hold any questions until the end, except any clarifying questions you might have. So now it is my pleasure to introduce today's speaker. Talea Mayo is assistant professor in the Department of Mathematics at Emory University, and she's an expert in the development and application of numerical hydrodynamic models for coastal hazards. She received a bachelor's from Grambling State University and a master's and PhD in computational and applied math from UT Austin. Afterwards, she was a postdoctoral researcher at Princeton and a professor at the University of Central Florida before joining the faculty at Emory last year. She was recently awarded the Early Career Research Fellowship by the National Academy's Gulf Research Program and an Early Career Faculty Innovator Award here at NCAR. Today, she'll be speaking about climate change impacts on hurricane storm surge risk. So Talea, feel free to go ahead and share your screen and take it away.
All right. Okay, you can see the slides.
Yep.
Okay, so I prefer to keep them like this just so I know what you see. So thank you for that introductions. And yes, today I want to talk about the work that I've done about climate change impacts on hurricane storm surge risk. And actually the second body of work I developed with Ethan Gutman, who's a scientist at NCAR through the Innovator Program. So just to give a bit of background, hurricane storm surges are a natural hazard that affect coastal regions. So coastal regions are the intersection of complex physical processes. So you have everything going on with the ocean, but then also the built environment. And so this makes it super interesting for me because there's direct impacts on people. The coastal environment is home to more than 40% of the US population, and this is expected to increase by more than 50% by 2060. So they're also at increasing risk of natural hazards, including floods and coastal erosions. Those are the two natural hazards that I've spent the most time studying. And then again, today I'll speak mostly to storm surges. So storm surges describe the abnormal rise of water generated by a storm, so specifically like a tropical cyclone. The abnormal rise is in reference to the astronomical tide. So if we are used to the normal high tide, the storm surge is what happens above that. And then the tide plus the surge is called storm tide. So that'll give you kind of the total amount of flooding. And that is kind of what we generally mean when we talk about storm surges. So you can think of storm surges as kind of the net result of surface wind stress. So the wind from a hurricane or a tropical cyclone pushing towards the shore, and then bottom stress kind of trying to keep everything in place or preventing water from coming onshore. And so these are kind of the two physical phenomenon that I've spent the most time studying. So my earlier work was developing mathematical methods to kind of estimate how do you represent the bottom stress. And that's because it's kind of the thing that fights the storm surge. Storm surges also pose the greatest threat to life and property from a hurricane. And for example, Katrina caused maximum storm surges of 27.8 feet. And then Ida kind of preliminary estimates caused 8 to 10 feet of storm surges. So the National Hurricane Center increasingly will explicitly describe the hazard that's coming from the storm surge itself. So as opposed to just discussing the storm and kind of how intense is it going to be, what category is it going to be, where's landfall going to hit, they also have a number of products warning the public and emergency managers about the specific storm surge hazard. So these tweets were issued during Hurricane Ida. So you can see this is the coast of Louisiana. And so it's kind of giving people a heads up about how much storm surge they might expect along their own coastline. So storm surges have had significant roles in some of the catastrophes in the US recently. So this is a photo of New Orleans after Hurricane Katrina. And that is actually the storm that really got me interested in hurricane storm surges. And so obviously the flooding caused there was not just due to storm surges, but also due to a levee failure that was caused by the storm surge. So the storm surges had a significant impact on the infrastructure, which led to kind of long-lasting and immediate effects. This photo is Hurricane Sandy. And so that storm hit the Northeast coast in 2012. And so this storm was particularly devastating because of the high population density of the Northeast region, and then also the critical infrastructure that was harmed, like the subway system and power failures. And then this is a photo of Hurricane Harvey, which happened, I think, 2017, maybe. 2000, yeah, or mid 2000s, let's say, because, and this storm was particularly devastating because of it was a compound event. So the storm surge raised the levels of Galveston Bay, and that prevented a lot of the drainage of the rainfall. So it was heavy rainfall that couldn't get out of the metropolitan Houston area because of the storm surge. So storm surge kind of exacerbated the effects of the rainfall. So one of the ways that we study hurricane storm surges are through numerical modeling. And so the mathematical model that describes storm surges are the shallow water equations. And so this shows conservation of mass and conservation of momentum. And so if you solve these equations, you can solve them for H and some form of depth average velocity. So H is the total height of the water column, or how much surge is in a particular place, and then U and V would be depth average velocities or the currents. And so solving this set of PDEs gives us one way to approximate what is the storm surge at various locations. So two of the models I use are the ADCIRC model and the SLOSH model. And so the work I'll show today use each of them respectively. So the ADCIRC model is a finite element model. And so if you look closely here, you're looking at the outline of the United States. So this is Florida. This is the Gulf of Mexico, and this is the East Coast. And so what we're actually simulating is kind of what's going on in the coastal waters. So not what's going on land, but what's going on next to the land. And so that allows us to understand what the storm surges look like. There are other meshes that actually go into the land so we can understand kind of what are the physics of what would happen over land. And so this model is, for, I guess, people who are interested, it's a finite element method, which allows us to kind of have more resolution near the coastline. And that is kind of the area that we tend to care about for our applications. The SLOSH model was developed much earlier, actually, but kind of the present version is described in this paper, this 1992 paper also. And so this solves a similar form of the shallow water equations, but the discretization is finite difference. And so what that kind of means in practice is that you cannot resolve closer to the coastline. So things kind of have to have the same resolution no matter where you are on a particular spatial domain. But how we get away with getting more resolution distribution towards the coastline is by solving things in polar coordinates. And so this allows us to have more resolution near the center of the mesh, or the basin they call it, as opposed to the outer radius of the basins. So both of these models solve some approximation of the shallow water equations. And then in the end, we have at least kind of what is the predicted water elevation at a given location. So within the meshes or spatial domains, based on whatever forcing we're giving the model. So we'll use kind of the storm or tidal signal as an input to the model, and then the output is the storm surge we can predict. Okay. So hydrodynamic models are used to forecast storm surges during hurricanes, which can guide emergency management and response. So this slide is a screenshot of the CIRA website, and this is just one example of how the ADCIRC model is used in real time. So as a storm is approaching the US coastline, then they will use kind of predictions of the storm trajectory and intensity to understand what might the storm surge actually look like. And so I call that real-time forecasting, but they can also be used in a different way, which is kind of for what I call longer-term planning. So the question is, how do we prepare for extreme events that seem to be occurring more regularly? So not just as one particular storm is approaching the coast, but kind of in general. How do we know how to build and prepare for intense storms? So this is kind of a question about increasing coastal resilience. And so the measures that we can use to predict or prepare for intense storms are can be kind of classified in 4 ways. So one is natural features, so preserving things that are already there that naturally diminish storm surge. So that would be like wetlands and marshes. And then nature-based measures would be kind of the implementation of something that's based on nature, but maybe not naturally there. So maybe pouring sand to create dunes and things like that. And then there's structural approaches, which we tend to be a little bit more familiar with. So like building flood walls to prevent surge that may come, and then non-structural approaches, which tends to mean policy implementation. So for example, mandates that people need to leave by a certain time, or mandates that people raise their houses, or flood insurance prices that would encourage people to do those things. Okay, so in order to develop kind of the appropriate measures for particular regions, then we need this kind of long-term risk assessment. And so that's part of what I'll talk about today. So when we're thinking about kind of what is long-term risk, what we do in practice is we model kind of the extremes. So if we're looking at kind of the maximum storm surges caused by a number of storms, then usually in other applications, we tend to care about kind of the modes or the things that happen the most. But for long-term planning and risk assessment, then we care about this tail end of the distribution, or in other words, low frequency, but high impact events. So we know, for example, you're not going to see a 4-meter storm surge very often, but when you do, the event or the impact can be significant. So that is kind of more what we're concerned about preparing for, especially as we know we'll be seeing more of these events. So the way that we do this is we model this tail through what's called the generalized Pareto distribution. And so I guess there's several ways you can model the tail, and then this is the distribution that we've used in this work. So this distribution, we define a large threshold. So kind of what are we considering the low probability or high impact event? And so in this example, it might be 2 meters. And then everything after that is what we're actually trying to measure. And so we can use software to kind of fit this data. Okay, so once we have the parameters, so fitting the data means we're coming up with this zeta, xi, and sigma parameters. And so that'll define kind of the model for the extremes. Once we have those parameters, what we can do is develop what's called a return curve. And so the return curve is going to define return levels in terms of return periods. And so in the end, we'll have something like this, where, for example, our 100-year flood is defined as about 3.5 meters. And so I always like to just take a second to reiterate what return periods actually mean. So return period is the measure of probability that a return level is actually exceeded. And so specifically, that would mean like a 100-year storm surge has a 1 out of 100 chance of exceedance each year, 1% chance of exceedance each year. So the name is a bit misleading because it doesn't mean that it's, has a 100% chance of occurring in 100 years. It means it has a 1% chance of occurring each year. Similarly, the 500-year storm has a 1 out of 500 chance of exceedance each year. So it's very possible and likely, or maybe not likely, but it's definitely possible to see multiple 500-year events in 1 year. And so I explain this a lot in kind of a paper in notices. So if we have the return curve, which is based on data that we've modeled with the Pareto distribution, then we're able to say something about the risk. And specifically, we can compare risk to other places and over time. So one problem with this approach, or this desire to have return curves, is that in order to model the extremes, then you need data there. And so kind of by definition, these events are low probability. And so we often don't have enough data to really come up with good estimates for these extremes. So historical data alone tends to be kind of unreliable in understanding risk, one, because there's not enough data, but also we know that the risk is evolving due to climate change. So it's quite likely the risk, even present day, if we base it on things that have already happened, then it's quite likely that it will be inaccurate, and certainly it won't stay accurate as the climate changes. So because of this, one of the approaches we've used for risk analysis is using synthetic storms. And so in the first body of work, we used 2,000 to 3,000 synthetic storms generated by a meteorologist for a given climate scenario. So what I'll show you is that the climate scenario can represent present day, but it can also be representative of the future. And so we have criteria that the storm come close to sites that we're interested in and has at least tropical storm strength. And so this is allowing us to kind of populate the end of this distribution that we want to model. So the climate scenarios that we focus on are kind of present day. And for that, we get data from the NSEP NCAR analysis, and then also end of century. And so here we used RCP 8.5 emission scenario of the IPCC AR5, so the fifth report of the International Panel on Climate Change. And so using these emission scenarios, then we can, along with these climate models, basically create these synthetic storms. So we used 4 climate models to create suites of synthetic storms, and then use those storms along with our storm surge model to understand kind of what do the storm surges of all of these look like. And then once we have those maximum storm surges, then we have something like this, which we can fit our generalized Pareto distribution, or we can model the tail behavior. So the storm data, just as an aside, like what do these storms actually look like? I'm going to show results for Jamaica Bay, New York. And so this is the distributions that came from the storms, the synthetic storms that were generated there. So the NSEP NCAR reanalysis, the distribution is this black line. And then basically all of the dashed lines are how the different climate models model present day storms, and then the solid lines are how do those same models model the storms at the end of the century. And so what you kind of see is like this shift to the right in maximum wind speed, and then also in the radius of maximum wind speed. So it's a little bit difficult to differentiate, but you can kind of see that, for example, these tails are thicker for the solid line. So we see more of the extremes. And these are two parameters that we know contribute positively, meaning they increase storm surge. So we expect to see increased storm surge risk. One thing that we also consider is the distribution of sea level rise. So in general, people or often will consider sea level rise in terms of like local mean sea level, but here we actually convolve the entire distribution of sea level so that we're also accounting for extremes in the sea level rise data. So the location that we focus on, or that I'll show you here today, is Jamaica Bay, New York. But we also did the same methodology for 3 other sites all along the East Coast. And these were identified by landscape architect teams because they were susceptible to inundation, but also socioeconomically vulnerable. So this was part of a larger project a few years back. Just to kind of understand what could be done to increase resilience for coastal communities like these. So the first result we have, so once we use the synthetic storms along with the storm surge model, we model the tail of the distribution of the maximum storm surges and then get the return curves. And so this is the return curve we get for the present day. So we'll call it 1990, present day storm surge risk at Jamaica Bay. And so kind of just to highlight maybe what you pull out of this is the 100-year flood here is 3.3 meters. And oh goodness, okay. Okay, the 100-year flood is 3.3 meters. But once we add the sea level rise predicted for the middle of the century, then we get a shift in this curve. So we're doing this convolution with the sea level rise predicted at the same place. And so we get this new curve. And if we look at what used to be the 100-year flood, which is 3.3 meters, we see that it becomes the 57-year flood. Or in other words, it becomes almost 2 times as likely in a given year. If we convolve the sea level rise information for the end of the century, then the curve moves even further to the left. And so what was the 100-year flood becomes the 29-year flood, or it's likely that it might be 4 times as likely in a given year. Another way you can think about these curves is kind of how is the 100-year flood changing? And so what was the 100-year flood today, which was 3.3 meters, by mid-century becomes 3.7, and then end of century becomes 4.3. And so if you were to build something or plan around your 100-year event being 3.3 meters, then very quickly you see that you've underestimated the risk. And that is just accounting for sea level rise alone. But what our methodology allowed us to do, because we're modeling the synthetic storms, we don't have to rely on historical data. We can also use projected data. And so what we can do is compare kind of how do those projections that come from climate change models change. So not just to sea level rise alone, but also to changes in storm climatology. So radius of maximum wind speeds, translation speeds, et cetera. So if I model the present day risk using, for example, the GFDL model, one of the first things you notice is that while it's not exactly in line with the NCEP model, but it still should give us an idea of how things are expected to change based on these models. So it underestimates the current 100-year flood by 20 centimeters. However, when I use the mid-century data along with the mid-century sea level rise, so now I'm not just accounting for sea level rise, but I'm accounting for the storm climatology as well. What was the 100-year surge moves to the 57-year surge. So again, or sorry, that's what happened with the NCEP data. So the solid line to the solid line, you were saying basically your risk increased by a factor of 2. But if we also include changing storm climatology, the dashed line to the dashed line, we're seeing it increase by a factor of 3. So the 100-year flood level is 3 times more likely if we also account for changing storm climatology. And if we look further out to the end of the century, for the NCEP data, so just accounting for sea level rise, we saw the 100-year surge become the 29-year surge. But now, if we also account for changing storm climatology, the 100-year surge becomes the 6-year surge. So the point of this is essentially that you do need to consider for sea level rise, but it's also really important that you consider how are the storms themselves actually changing. So if you assume kind of we'll see the same types of storm at the end of the century or mid-century that we've seen historically, then you'll underestimate your risk even further. And so this is kind of a screenshot from the related paper about the decreases in return curve. So this is 50-year on the top left, 100-year on the top right, and then 500-year 1000. And so this is showing in present day, maybe what's considered the 50-year flood is here. And if we add the sea level rise distribution, convolve the distribution, so we account for the fact that there should be sea level rise by the end of the century, then it gets reduced. So here to something like a 25-year flood. And then if you also consider how do the storms change, then it reduces even further. And so what you're seeing here is that all of these return periods are decreasing. But if you only consider sea level rise, then you underestimate the decrease. Of course, there's kind of some variance in how much they decrease depending on which climate model is used, but all of them show that the storm climatology plays a role. So all of this was part of a project called Structures of Coastal Resilience. And so that website is still active. The kind of landscape architecture part has been published in a book. And so that came out in 2018. And then I have a paper that's under review right now that kind of discusses more of the modeling aspects. And so it's for every site, we produce all of these plots. So not just kind of what happens at one place, but then we also kind of use DEMs and the modeling framework at many more locations to create the surface. And so what you're seeing is over time, your risk is increasing. So this is showing this second line is the 100-year flood. So you're seeing the 100-year flood spatially extending further and further back over time. So the probabilistic modeling framework depends on these synthetic storms, which we're generating from a statistical model. And so computationally, the cost can be prohibitive. So we're running 2,000 to 3,000 simulations, storm surge simulations for each of those models. So in the work that I showed, we had 4 different models, 2 different time periods, at 4 different sites, right? So if you're doing 2,000 to 3,000 for each of those, then it's very expensive to run the storm surge models. And so that's one of the reasons that we use the slosh model for that project. But if we try to look at how risk is changing deterministically, then we're able to use a higher fidelity model. And we did this in the work with Ethan at NCAR by using WRF data. So in short, we imposed a climate change signal to WRF, which you may be familiar with, and then compared kind of how do storms in the present day compared to storms at the end of the century, and deterministically modeled the storm surge from both to compare. So the WRF model is the part that Ethan did. So it's 3D, it's convection permitting, and it's a regional climate model. It's very high resolution. So it's 4 kilometers in the horizontal direction, and then it has 51 vertical layers. We again impose the RCP 8.5 climate change signal, and we impose this on the boundary conditions. And then we simulated 21 hurricanes that occurred from 2000 to 2013 under both present day climate conditions, but then under the RCP 8.5 emission scenario. And so that work is what Ethan contributed. And so that is published in his paper from 2018. So essentially at the end of it, we had 21 hurricanes that occurred and those were simulated using WRF, and then also what those same hurricanes would look like at the end of the century. Once we had those storms, then we're able to use a storm surge model to understand what does the respective storm surge look like from those storms. And so here's some details about the framework we use. So we use a standardized mesh called HSOFS. It has 1.8 million vertices, which basically means we're solving this shallow water equations in 1.8 million places. And it also has overland grid resolution, which I mentioned. So not only are we solving for the still water heights out in the ocean and the Gulf, but also overland. And so that gave us the ability to kind of understand what's happening in coastal regions. So this is just one example, Hurricane Ike. So this is Hurricane Ike measured or modeled using present day climate conditions. So this is the storm surge, and this is, I guess, Houston and Houston metropolitan area. And so kind of what you can clearly see is, well, there's red. So red is higher levels of storm surge. And then we did the same thing using the end of century Ike. And then just from the eyeball perspective, then you see that there is more storm surge, significantly more red. And so just to quantify it a little bit, the inundation volume or the volume of floodwater that's now over land was 23 cubic kilometers for the present day Ike, and then that increased to 30 cubic kilometers by the end of the century. The inundation extent, so if we just look at kind of the area that's being impacted, so what was dry becoming wet, went from 16,000 square kilometers to 17,000 square kilometers. And I should emphasize that here we're only looking at storm surge. So this doesn't even account for projections of sea level rise. This is storm surge alone. We did the same thing for all of the 21 storms and then just kind of created this composite showing what were the overall changes. And so what you should gather from this figure is that there's a lot more red than there is blue. So for the storms we looked like, on average, most of them were causing increases in storm surge by the end of century. There's a few places where the storm surge decreased, but overwhelmingly we're projected to see more storm surges from the same storms just because of climate change. So this is a list of all of the storms that we looked at. Right here, they're ordered from the control or the present day volume inundation. So they're decreasing. So Ike was quote unquote the most severe storm by this metric. And then Isidore, and then Rita, et cetera. And then we're also here looking at then what was the volume inundation for the end of century. And so you can see that on average, there's an increase and there's like a 36% change. You can also see that there's a few places or a few instances where there's actually a decrease, but overall, we expect that there will be larger inundation volumes expected. And then here is a figure that we made kind of describing the changes in volume. So that's what this last column is, but compared to how do storm characteristics change. So the red is supposed to represent something becoming more intense. The blue is becoming less intense. So for example, Ivan is expected to become more intense in wind speed by the end of the century. However, we see that the storm surge doesn't necessarily become more intense, as opposed to the storm's outer or radius of maximum wind speed becomes less intense, which here would mean smaller. However, that seems to kind of take over the overall inundation volume. So what we found when we actually started looking at the specific storm characteristics was, yes, there's an overall expected increase in the amount of flooding or inundation or storm surge impacts, but it's not clearly related to one particular storm characteristic. So in other words, we can't just say, well, if a storm's wind speed is expected to intensify, or if we expect that overwhelmingly maximum wind speeds will increase over the century, doesn't necessarily mean that the storm surge would also increase. And this is largely due to kind of changes in tracks, and so maybe where the affected areas are. Another thing we did was kind of look at not just the change, but just the characteristics themselves. So if we look at, for example, present day storm characteristics, here's the storm surge volumes, again, in increasing order. So Ike, again, the most intense, then Isidore. But, you know, if we look at something like maximum wind speed, then we might expect to also see this gradient where things are going from less intense to more intense. And again, we saw that that's not what we're seeing. And the same thing is observed for end of century data. So there's not a direct correlation between distinct storm characteristics like wind speed or radius of maximum wind or translation speed, and the amount of impact or volume of inundations that can be expected. Kind of our conclusion from that is then we need to model physically what is expected to happen. We can't just assume based on statistics, if this gets worse, this will get worse. And so these results of this study were published. I think this is actually it was published in 2020. I need to fix that. So just some concluding thoughts. Surge is a low probability, high impact hazards. How low is greatly impacted by the expected tropical cyclone frequency, which is uncertain. So if you recall the figure that I showed about this 100-year storm, what is its return period by the end of the century, kind of varied based on the climate models. And that was the major difference that we were able to see. The ones that predicted kind of less of an increase in risk, those climate models also predicted lower tropical cyclone frequencies. However, how high the impact is dependent on a lot of things. So for example, tropical cyclone intensity, size, translation speeds, and the uncertainties in all of them. And then also kind of other things that are dependent on the storm. So for example, Katrina, the impact was due to levee failures. For Sandy, the impact was due to population density. And for Harvey, it was due to the precipitation from the storm and also the infrastructure there. So a lot to do with kind of how much had been built. And so I think kind of one thing we can learn is that numerical storm surge modeling is needed for risk assessment, but it's really just one component of a lot of other things that can affect the true impacts. So I guess with that, I will take any questions that there are. Thank you.
Excellent. Thanks a lot, Talea. We have some time for questions. And again, feel free to put them in the chat, or you can just raise your hand and I will go ahead and call on you. So we have a couple of questions already in the chat, and I'll start off with David Nolan, who asks, why do you use the NCEP reanalysis for the hurricane climatology? Could you use the official best track data sets from the National Hurricane Center?
So I think I've done some other work where we use best track data. So best track data has to be modeled parametrically. So it just includes like a limited number of parameters. And so you can certainly do that, but here we use gridded wind data. I think that's the main benefit of using reanalysis work. So we get kind of less of the uncertainty that comes from the parametric wind modeling. But I think you could use best track data if you're willing to sacrifice the wind modeling. Yeah. Yes. Okay. And I have a paper that discusses parametric wind modeling, so I'm familiar, but that project specifically I didn't design, but I see that as one of the advantages.
Great. Julio asks, will increasing precipitation in storms have any impact on storm surge impact?
Yeah, so storm surge specifically refers to coastal flooding. So it should, by definition, it's not going to be affected by precipitation, but what it can impact flooding. So precipitation causes what we call inland flooding. So you have the flooding coming, overland, kind of going towards the ocean, and then you have the storm surge that's coming from the ocean. And just like in Harvey, these things can interact into what's called compound flooding, so they can affect each other and occur at the same time. So in short, I would say increasing precipitation will affect flooding, but not what we call coastal flooding. It doesn't affect the surge. It can affect the amount of water.
Thank you.
All right. Melissa says, thanks, Talea. In addition to changing storm characteristics and sea level, how important is the timing and magnitude of tides to surge extremes? If I understood correctly that your scenarios don't directly include tides, I'm misreading too. I'm curious if the 18.6 lunar cycle and tidal magnitude would significantly modulate the surge tail, for instance, in the 2030s.
Yeah, so to clarify, the latter study we didn't include tides. So that was storm surge alone, the one where we used WRF. The earlier study, we did use a predicted tide, but we used kind of the present day predicted tides. And I'm not sure what is the latest research on how will tides be affected. So the way we represented them, we did them random. So we assumed that we basically simulated the entire storm surge, and then we added on a tide, but we randomly chose the point in the tidal cycle it would start. So tides are included probably very accurately in the present day analysis of the storm surge risk that I showed in the first part. For the latter, tides are not included. And I don't know, honestly. Like I haven't thought enough about this. Just kind of how do lunar cycles or how does the changes in tidal magnitudes would affect? But it seems it would, right? So if all of your extremes became a little bit, or if all of your values became a little more extreme, it seems like there'd just be a shift in the curve. I guess maybe what I'm not sure about is the change in the return period. Like, would it kind of wash out if they're both there? But I guess in short, I'm not really sure. I think that's a good question to think about.
All right, Katie has a hand raised.
Thanks for the really interesting talk. I have maybe a less technical question that's kind of about how to communicate risk. And I'm wondering if you have thoughts on using return periods in general, because as you've shown with climate change, that number is sort of changing. So are there other ways of communicating risk that are maybe more intuitive or less of having to sort of shift that calculation in your head? I'm just curious if you've thought about that at all.
Yeah, I guess I haven't thought about exactly what we should do. I've thought a lot about, like, are we effectively communicating risk? And so some of the work that was supported through the innovator program, we were actually kind of surveying literature and had intended to do some interviewing to survey people about risk maps and what means more to them. So I think definitely the terminology is pretty confusing, like 100-year flood. And I see quoted a lot of times where people say like, oh, we've had, 300-500-year floods in a short time. But I think the way I would answer that is I think it's a good area for research. Like I think it definitely needs to be supported research that's trying to figure out how to best communicate this information to the public is really important. So the paper that I cited, this one, the lasting impacts of the Saffir-Simpson scale, we kind of started to dig into that, just kind of how do people understand risk and like what is hindering risk. And in writing that paper, we came up with a whole host of questions like, oh, these are actually the things, all of the different things that make risk difficult to understand. So I think it's important, and I think probably something should be changed. I can show maybe around here how NHC has kind of like for short-term risk or like immediate threats have definitely developed projects or products to communicate what is the risk immediately. But as far as long-term risk and like encouraging people not to move to certain areas, or at least being aware of what risk they're putting themselves at by staying in areas or developing in areas, I'm not sure. I think it's important.
Thank you.
Yeah.
All right, Jimmy asks, is the return period applied to local positions or large lengths of coastline?
Yeah, so in the work I showed, it is a local position, like there's a specific lat long, and then it corresponds to, in the modeling, kind of, I'm taking storm surge data from a specific place. But what we did in the project, so the website that I referenced, we did that across a whole domain. So if I showed here, these maps, so those numbers correspond to a specific lat and long, the ones that I showed in this talk. But in this body of work, then we did it all across the domain. I hope that's answering. So I guess what I'm saying is that those specific numbers I gave you are a local position. But if you repeat the methodology for the stretch of coastline, then you have it across the stretch of coastline.
All right, and I had a question about the sort of fat tails that you get for the extremes and how that changes. I guess one question was how much of the extremes that you see in your synthetic experiments comes from like the dynamics of the hurricanes themselves, and how much might come from possible extreme or unlikely low frequency climate states?
Can you say that again?
Yeah, I was wondering, so you'd run these synthetic experiments in kind of
Right.
the modern and then end of century. And I guess, like I'm wondering if there's any impact on like the state of the larger scale climate, which, changes from internal variability and stuff. Like if that has an imprint, if those extremes are translated into extremes in hurricane variability.
Yeah, I think I understand what you're asking. And I'm going to say that my background's definitely not meteorology. However, we're defining, so in the GPD distribution, what we do is we define this threshold. And so and then we're really modeling what's extreme beyond that. So I think if you're talking about kind of like variability in climate as opposed to like an actual extreme event, I think it would be very difficult to get out here just from the former. Does that make sense?
Yeah, that does. Yeah, I guess it was partly a question too about when we see, so when in these synthetic experiments, when you're kind of way out in the tail, is that mostly because of something that's happening within like an individual hurricane storm track that's sort of acting in kind of like a time mean, like larger scale pattern of sea surface temperature, for instance, or for instance, if you had some unlucky confluence of an El Nino year and certain phase of large scale, if that might have an imprint too. That was
right.
I guess, yeah.
Yeah, no, I think it's the same answer, because here I use as the threshold the 100-year flood, like empirically. So it's like I'm only looking at like the very extreme events, and I don't think you can get that level of surge from, something not extreme.
Great, thank you. All right, well, if there aren't any other questions, then Talea, thanks once again for an excellent talk. And everyone, I'll look forward to seeing you again next week. Take care.
Thank you.